Hello, Startup Central. My name is Eli Bingham. This is my colleague, Alex Favreau. We both work on the risk engineering team at Affirm. And today we're going to talk to you about our lending business. How and why we use data and machine learning to power our risk management, and some of the technical challenges involved in that work. So, the first time I meet someone, they often ask us, where do you work? This just happened today, actually. And when we tell them, we work at a firm, they usually ask, well, okay, but which firm do you work for? So, Affirm was founded in 2012 by Max Levchin with a mission to build honest financial products from the ground up using software and data. We started with consumer credit with the belief that credit is a powerful tool that can be extremely useful for consumers, but is also dangerous when it's misused. So Affirm seeks to strike a balance between that power and the safeguards on it, and not to base our profitability on bad things happening to our users. We've invested technical resources into ensuring that we only offer our customers what they can reasonably afford. We only make money if our customers pay us back, so our success really relies on our customers' success. And before a customer agrees to pay for their purchase with Affirm, they know exactly what they'll pay each month, and they can rest easy in the event they can't pay us on time, and that they'll never be charged a late fee. But this commitment to fairness and transparency means that we have to excel at risk management. We have to do a better job than the industry standard in deciding who we should lend to, for how long, and for how much. And our scale and growth also imply that we have to use automation, data, and machine learning to achieve that goal. We have tens of thousands of people applying for installment loans with Affirm every day, and that makes it totally infeasible to have human beings reviewing each application and deciding what risk looks reasonable. Our volume has roughly doubled every year since we launched our first product. Last year, we originated roughly $1 billion in small loans, and we expect our past performance to continue. So in this talk, I'm going to start with a short overview of how our business works today, the role that data and machine learning play in our decision-making process, and some of the technical challenges that come with that. I'm then going to turn things over to Alex, who will discuss some of our solutions to these problems, and in particular focusing on how we use AWS and EMR to help us scale and manage our decision-making systems. So, how does Affirm work? Our core product is an installment loan for a considered purchase, offered to the customer online directly at the point of sale as a payment option when they're checking out. Casper, Peloton, Wayfair, and thousands of other merchants integrate directly with our system to offer this choice to consumers in their checkout process. And I want to emphasize here that we underwrite the loan live at the point of purchase as the customer is checking out. So making these decisions in real time is critical to both the success of our product as well as the success of the merchant. To illustrate this, I'm going to walk you through a typical Affirm workflow and how we use data behind the scenes to power that workflow. So imagine that you're buying a mattress from, say, Purple or Casper or Nest Bedding or one of our other partners, and you're ready to check out. The merchant will present Affirm as a payment option alongside credit cards, debit cards, and so forth. And provided the user selects Affirm as their payment option, they're directed to a simple loan application. First, they have to verify their device using a mobile phone, and we send an SMS message to the number they provided and ask the user to verify the code they received. And next, the user enters their personal information and consents to Affirm retrieving data about them from third parties like a credit bureau. So it turns out that the limited data we get from our users is not much to actually go on in terms of underwriting their application. But we can use their phone number to look up information about their device. We can use their personal information that they provided to look up information about their credit history. And we can use their address to look up information about their billing address, as well as whether asking to ship their purchase. If an example would be if these two addresses don't match, this could signify fraud. Additionally, if the address the user provided doesn't match the credit report, we wouldn't be able to confirm their identity. So this raw information is transformed into signals we've identified as important for our decision-making systems and our models, and then is passed to those systems where we have to make a number of real-time decisions. So the first decision is, does this individual really exist? A common form of fraud is a synthetic identity theft, where fraudsters will construct false identities out of a mix of different stolen data from real individuals, as well as completely fake data. The second decision we have to make is the individual applying for the loan actually who they say they are. Many of us are familiar with identity theft. There's an online marketplace for stolen identities that fraudsters can leverage at scale, often with extremely rich identifying information, such that ordinary security checks can be overcome. So, in other words, if this goose is claiming to be a penguin, how do you know it's actually a penguin? And finally, we have to decide, does this individual have the capacity, the willingness, and the intent to pay us back for the amount of money that they've requested? And in many ways, this is a harder problem to solve than the fraud problem, since a fraudster is lying to you, but in some sense, someone who can't pay you back is lying to themselves. Assuming that we can approve the loan, the user is presented with a simple range of terms and prices and is then able to select a repayment schedule based upon their personal budget and the desired repayment schedule. There's no hidden fees, no gotchas. We don't change the terms during the course of the loan's lifetime. And unlike a revolving line of credit, the loan is payable in fixed installments over a fixed set of terms, and we use simple rather than compound interest. So, making this work at scale with high accuracy and low latency has two core technical challenges that we've had to solve. The first challenge is maintaining the integrity and correctness of the data that's actually driving this decision-making system. And this requirement is not just required online, but it's also offline, where our machine learning models are trained and data analysis drives our product decision-making. Skew between training data and serving data, that is the data the model was trained on and the data that the model actually observes when it's making a decision, can result in millions of dollars being lost, in violation of lending regulations, in loss of reputation, and generally existential risk. And because we're making decisions that move money around and must deal with regulatory and compliance considerations, and with Affirm as a company actually being on the hook for the risk of the loan that we're making, the tolerance for error in data is extremely low. The second challenge we have that we want to talk about today is obtaining ground truth about the accuracy of our models is very slow, especially in credit. So unlike in a fast-moving space where machine learning is used like ad tech or social media, where if you have an issue with your model, that might show up in a CTR metric in a matter of minutes or hours, it can take us up to 60 days to get a delinquency label for a loan payment. So problems with live models and decision-making systems might be very difficult to detect in that interim. So now I would like to turn it over to Alex, who's going to talk about how we've addressed these issues in detail.
Thanks, Eli. So as Eli mentioned, there are a few decisions we need to make in real time when we're assessing the risk of a loan applicant. We do this automatically with a combination of machine learning models as well as hand-coded business logic that we execute against data pulled from a variety of both internal and external data sources. So for this part of the talk, I'm first going to discuss how our decisioning code is structured, and then a system that we built for regression testing that allows us to deploy changes to that decisioning code with confidence. And then I'm going to go into some of the additional data challenges presented by deploying machine learning models to solve these same problems. So at Affirm, we have tens of thousands of lines of business logic that go into our risk management decisions. As you might imagine, a big challenge for us is to be able to confidently make changes to that code without introducing any regressions. So although traditional testing methods have helped us a lot, it's really hard to ensure that we have exhaustive coverage of all the possible cases. So to help address this problem, we developed a system that allows us to replay real production decisions with a new version of the code before we deploy it and verify that we only see the changes that we expect to the final decisions as well as their intermediate results. So to build this system, we first had to refactor our code base to separate the I/O, which fetches the data that we use to make these decisions, from some stateless business logic, which implements our risk management policies. This gives us the flexibility to run different versions of the core decisioning logic in a separate environment, which looks a little bit different from our production web service. So we'll see later how that's helped us to build this regression testing system. But for now, here's an overview of what our production decisioning service looks like. The service responds to requests from our loan application flow in real time, and it fetches data from a variety of both internal and external sources, and then it passes that through to our risk decision library, where the bulk of the business logic is actually implemented. So taking a peek at this library, this first performs some transformations of the data to produce what we refer to internally as signals. So these are like simple pieces of data that are derived from the more complex upstream raw data. And examples of this might include like a FICO score from a credit report, or maybe the number of loans that a user has successfully repaid. These signals then get passed into various sets of hand-coded business rules that we refer to as policies. And these policies are composed with one another until we reach a final decision. So here's an example of a particular policy. This is a policy that just checks whether the user is over 18. You'll notice that we've actually written our own DSL for implementing these policies, which is the syntax that you see here. But I'm not going to go too much into that in this talk. So once we run all these policies, then we get a final decision. And we take that decision and we log it. And in that log entry, we include all of the raw data that went into the decision, all of the signals that were resolved from that raw data, and then all of the policy results that, the intermediate policy results that resulted in the final decision. And then these logs get periodically rotated to S3, where they can be consumed by other pieces of our system that I'll talk about. So with this architecture in place, we were able to build a code verification system that reads these logs and feeds the raw data into the exact same library that the service uses to make decisions. So again, this separation between the I/O of the service and the logic of the library makes it straightforward for us to test new versions of the library against real production data that was used for previous production decisions. And the output of this system is 2 reports. And these reports describe differences in the decisions made by the new version of the library and what actually happened on production. So this includes signal value changes and in the signal report, and then there's a policy report which tells you what changed in the policy results. So I'll discuss the format of these reports in a little more detail later. So if we zoom out here, we can see where the library is invoked both in the online service and then in our offline verification system. And in particular, we can see how this setup lets us test a new version of the library offline and see what changes about real production decisions before we ship that code to production. This gives us a very high degree of confidence in the changes we're making to our risk decisions before the new code lands in production. So since we're at the AWS conference, I should also mention that we use Spark running on EMR to test these prospective code changes against tens of thousands of recent production decisions, and we do this before every release. As I mentioned earlier, these logs get rotated to S3, which makes this a very straightforward architecture to build on. Cool, so let's run through an example. Here's an example of some logic which derives some signals from a structured piece of data, in this case a credit report. So we declare some dependencies at the top of the resolver, which is the data that we're going to use to resolve the signals, and then a list of signals that we're going to resolve from that data. And then there's a resolve method which actually does all the logic and pulls the signals out of the raw data. So suppose now that we're making some change to this resolver and we accidentally include this line, which is changing the FICO score that we pull off of the credit report. When we run this change through our system, we get back those two reports I mentioned earlier. The first one is the signal report, which shows us the signals that changed, the number of decisions for which that signal value changed, and also a summary of what happened. So here the value decreased. Note that we don't include any of the actual signal values themselves in this report, since those can contain potentially sensitive consumer information like a credit score. And the second report, the policy report, shows us the intermediate policy results which differed from what actually happened on production. So this is particularly helpful for understanding why some decision was different across the code versions. Why do we have both? A lot of the decisioning logic is dependent on the signal resolution, so it's helpful when testing changes to understand exactly why the decision that we get is different, and to make sure we're also not masking any unexpected behavior, even if the final decision itself is the same. So this system has become a really invaluable part of our workflow, so much so that we've actually gone ahead and integrated it into our CI system. So now for any code changes that touch our risk decisioning system, in addition to all of our standard unit tests, we also kick off this verification system, which checks the changes against production decisions and then delivers the reports to the developer. And so we can see these reports in our code review tool, and then also, once again, when we do a final check before going to production. So here's a diagram of a typical CI setup. How do developers typically consume these reports? If you're just refactoring something, it's really helpful to confirm that nothing functionally changed about any of the decisions that we're making. And if you do actually want to make a change, like if you're fixing some bug, you can confirm that only the decisions that exhibited that bug were actually changed by your code change. So we've also written a blog post that describes the system in a little more detail for anyone who wants to check that out, and you can find that at tech.affirm.com. Cool, so now I'm going to switch gears a little bit and talk about some of the related data challenges that we've had to deal with working on machine learning models in this area. So here's a high-level overview of a typical supervised machine learning system. We have some labeled data that comes from elsewhere in our system that we use to train models. These models are deployed to production where they're used to make predictions about new unlabeled data. In our case, this happens within our web service whenever we need to make some kind of risk decision. And so a typical problem that can arise in these systems is called training serving skew. So for these models to work, it's critical that the features used when training the model are exactly the same as the features that we use when we make predictions about new data. A related problem that also occurs when you have some time delay before you get labels for your data, for example, if you're waiting for a loan to be repaid, is when information from the future leaks into your training data. This is a problem because it lets the model effectively cheat at training time, which may cause it to learn the wrong effects from the data. For example, if repayment data from the loan that you're currently underwriting is somehow included in certain features, then the model may overestimate the importance of those features. So one possible solution to both of these problems is to log the features that go into the model whenever you make a prediction. And then we can use those logged features to train new versions of the model. This effectively guarantees that you don't have any data from the future making it into your training set, and it also gives you some assurance that the way you derive those features for training is the same as when you derive those features for making predictions. It's still possible, however, that the logic you use to extract those features changes over time. There might be some drift. So to protect ourselves against this, we can actually use that verification system, which I just described, where instead of signals, we're now just dealing with features of our machine learning model. But this strategy presents another problem. How do we add new features to the training set? So for example, suppose we discover some correlation between the velocity at which users are taking out loans and repayment. How can we incorporate that information as a feature in our model with this approach if we didn't include those features and log them when we originally made the predictions for those loans? This is also known as the backfill problem, where we don't have log features for a particular training sample, but we still want some particular point-in-time accurate features that are consistent with how new samples will be featurized for future predictions. So this diagram shows how a training set can evolve over time. As we get new samples, it's fairly straightforward just to add new features to the training set and log them with those samples. But we need some separate process for adding these new features to the historical samples. So our solution to this is to use the exact same decision log that I mentioned previously in the talk to provide a point-in-time snapshot of the input data. And again, signals now are just the features of the machine learning model. This lets us run the exact same featurization code when we add new features to historical samples that we use to featurize new samples for prediction. Again, giving us some confidence that we don't introduce training serving skew as we add these new features. And as I mentioned previously, we can also rerun the featurization logic over historical samples to catch code regressions to make sure there's not drift in this logic. So the next obvious question is, what do we do about new data sources? As I've described it, this system only works for adding features to data that was already logged when we made a decision. So what do we do if the data is not logged? For external data sources, so this is data that we get from third parties, typically the way we do this is we start logging the data when we're making decisions before we started using the data. And then later we'll go and develop features for it to incorporate that into the model. So at a high level, the process looks like this. We start logging the data at decision time. We go and do some analysis, develop some features over it. And then we can go back and run the featurization code that we just developed over the log data to backfill those new features onto the samples for which we collected that data. This unfortunately means that we won't always have all these features for our entire training set. We just won't have the data for any samples where we made decisions before we started logging it. But it's the best that we can do unless we have some other way of sourcing this data. For internal data sources, so databases or tables managed by other teams at the company, we usually do have a full historical record. We just need to make sure that we are sourcing point-in-time accurate representations of the data from whichever team owns it. So usually we'll just go to the team that owns the data and say, hey, we need this data from this particular point in time. We also have some company-wide practices like periodic table snapshots that can be used for this purpose, again, to make sure that we're not leaking data from the future into our training set. So we still have to go through the trouble to make sure that the data is temporally consistent, but at least with this framework, we have some assurance that the featurization is the same both when we generate the training set and then when we make predictions online. So where does AWS come into this? Going back to our backfill diagram, this is not really scaled appropriately. A more appropriate scaling might look something like this. And what I mean by this is that running a backfill of new features typically involves working with much larger quantities of data than just incrementally adding new samples to our training set. So the amount of computing resources that we need to run a particular job can vary pretty drastically depending on whether we're just adding new samples or adding new features to our entire historical training set. So building this pipeline on S3 and with Spark on EMR has allowed us to decouple our storage from our computing resources. And then by managing the lifecycle of those computing resources with a specific job, we can elastically scale to meet the demands of that particular job. We've made a few other design decisions that allow us to do this more efficiently. One is to use Parquet as a storage format for these decision logs I mentioned. So this is what the Parquet format looks like. It's a columnar format, and it has a few nice features that we can use to optimize these jobs. For example, we've chosen to store the raw data from each different data source in its own column. And then this lets us use column projection to read and decompress only the parts of the decision log from which we'd like to extract features. Another feature that we get for free with this design is data partitioning. So we've chosen to partition our decision log by date so that if we need to backfill new features over a particular date range, Spark will automatically prune the partitions we don't care about in order to save on I/O cost. So these two features are really a big help when we need to backfill new features for example, some new data source that we might have for only like a relatively short period of time compared to our entire historical training set. So we can look only at the data that came from that one source and only over that particular time range in order to add those features to our training set. Cool. Finally, this wouldn't be a tech talk without a hiring plug. So if you're interested in working on these types of data problems, definitely check out our careers page. And if data problems aren't your thing, we also work on lots of other complicated problems up and down the stack. So there should be something that suits you. Thanks, everyone.
Cool. Thanks, guys. Let's give them a hand.